Greetings and welcome to this problem in material science regarding cold working. Now, cold working is the lower temperature deformation of metals, and that can be done through forging, rolling, extrusion, drawing, these different processes cold work a material. When a material is cold worked, there are many dislocations that are developed. These dislocations run into each other and stop the material from plastically deforming, causing it to have higher stresses before it fractures. This effectively strengthens it. So in this problem, we are given two specimens of the same alloy, and they're cylindrical, and they are previously undeformed. So that means they're not cold worked, and we're going to assume that they are annealed, basically with zero cold work. So other things that we are given include that the initial and final diameters, well, we're actually given the initial and final radii, but nobody measures the radii of a sample. You always measure the length and width if it's rectangular, or you measure the diameter. So I don't know why they gave radius. So I'm going to use diameter here, and going to fill that in with the first specimen. The first specimen had an initial radius of 16 millimeters, so I'll write that in as 32 millimeters, and it was cold worked down to a radius of 11 millimeters, so our final diameter is 22 millimeters. It's also given that the second specimen had an initial radius of 12 millimeters, so that means that it had a diameter of 24 millimeters. So these are all the givens. What are we trying to find? We're trying to find the second specimen's radius after deformation. I don't care, we'll just go with the diameter. After cold working. But what we want to make sure of is that the second specimen has the same cold work as the first specimen. So we're going to find the diameter of the second specimen after cold working it to the same as the first. So that means that the first thing we need to do is find out how much cold work the first specimen had. Well, we use our cold work equation here. So percent cold work is all about the area, not the diameter. So in order to find cold work, we need to find the area. In order to find the area, we need to find the diameter. So our percent cold work is simply the percent change in area. So it's the original area minus the final area over the original area. So we're just comparing it to what we started with. And to fill out the full area formula, we have pi times the original diameter squared over 4 minus pi times the final diameter squared, all that over 4. Take that whole thing and divide by the original area, which is pi times the original diameter all over 4. Now, this looks pretty annoying. So what we're going to do is, instead of actually finding those areas, although that's possible and that might be helpful depending on what you're trying to do, I'm going to use the power of algebra and simplify all this. I'm going to factor out pi over 4 from the top pi over 4 times dO squared minus pi over 4 times dF squared. So pi over 4 times dO squared minus dF squared. All of that over pi over 4 times dO squared. Notice how these two can cancel out. So pi over 4 cancels out with pi over 4. So our percent cold work equation boils down to this. dO squared minus dF squared all over dO squared. So now I'm actually going to plug these values into it, and we will have 32 millimeters quantity squared. Make sure you don't think it's just square millimeters, minus 22 millimeters squared all over 32 millimeters squared. And I end up with 52.7% cold work. So although the diameter did not drop by half, our area dropped by more than 50%. So I need to make sure that we use the same amount of cold work for our second sample. Well, I'm going to go back and use the power of algebra and solve for our final diameter. See, I'm going to go back to here, fill this in, and going to use this formula here, and instead I'm going to solve for that final diameter right there. So I'm going to put this down first. So we've got our initial setup here. Now I'm going to multiply through by dO squared. So that was by multiplying both sides by dO squared. Then I'm going to subtract dO squared from both sides. And I should get negative ds squared equals, I'm going to write it like this, minus dO squared plus dO squared times cold work percent. Then I'm going to multiply both sides by -1. Remember, the entire thing by -1, and I get df squared equals, got to multiply this by -1, and I just get dO squared. Then this has to become negative, minus DO squared times cold work percent. Before I solve straight for DF, I'm going to factor out the DO squared. So I've got DF squared equals DO squared times 1 minus cold work percent. So I just factored out this DO squared and this DO squared here. And it's nice to do this because we start with 100%, subtract another percent, and it just makes it easy. And you can kind of see the relationship a little bit better here. So then, last but not least, take the square root of this, take the square root of this, and we get df equals do times the square root of 1 minus the percent cold work. Now if we plug this in here, we're going to plug in our initial diameter and our percent cold work. Makes it pretty easy. df equals 24 millimeters times the square root of 1 minus 0.527. That gives us a final diameter of 16.5 millimeters. So we can now enter that in right here, 16.5. However, another way that we can approach this is simply by looking at these ratios here. My initial diameter to my final diameter should get a certain percent cold work. That ratio should be the same here. So I find that if I take my diameter of 1 initially divided by the diameter of 1 final, that should be the diameter of 2 initial divided by the diameter of 2 final. So I'm looking for diameter of 2 final, so I'll rearrange this. Diameter of 2 final equals diameter of 2 initial times diameter of 1 final over diameter of 1 initial. And if I plug my values into this, diameter of 2 initial is 24 millimeters. Multiply that times 22 millimeters all over 32 millimeters. You end up with exactly 16.5 millimeters. So that was an even shorter way of getting to where we wanted to go without even having to actually calculate the percent cold work. But it should be shown that we have the cold work calculation in here. So to summarize, we started with 2 specimens that were different diameters, but they had the same alloy and they were previously undeformed, or we assumed that they were annealed. They're cylindrical, so they're both circular. We got to keep that cross section going. We showed how to calculate the percent cold work and then use that to develop an expression for where we wanted to go to have the same cold work for a different diameter of the same material. We found that diameter and then showed a different way of going straight to that same diameter. I hope this increased your understanding of material science, and I hope that you are able to check out some of the other videos, and if you need any more help. Thank you very much.